He's turning this on. Unfortunately, today's class is short, so you're not getting sort of the warm-up and intro that I give in the full class. I'm just going to cut right to the examples. But it will be online, so you'll have access to that if you need to see it. Tonight's homework is just going to be a couple problems to make sure you followed what's going on in the lecture. This lecture is a little bit abstract, so it may be kind of hard to wrap your head around, so it may not be a bad thing to watch it a couple times. But what we're doing today is Riemann sums, which is a way to find the area under a curve. And this is a problem we did last class with one easy example. I'll give you like a rectangle, triangle, circle thing, and you're able to find that area just by doing geometry. But in general, if you have like a parabola or even the sine of x, simple geometry doesn't suffice. But we briefly discussed that one method that would work is drawing a bunch of rectangles, and the smaller those rectangles get, the closer your area is going to be. Well, a Riemann sum is a way to do that. We draw a bunch of rectangles, and we can actually mathematically draw infinitely many rectangles and compute the precise area. This is not something we'll be computationally doing a lot, but it lets us prove the first fundamental theorem of calculus, which tells us ultimately to find all these areas, all we have to do is take an antiderivative. So the main reason today's lecture is important is not so you can do these computations by hand, because we won't be doing that a lot. But what is important is so you can understand the proof of FTC1, which we'll do next class. So I got about 4 examples of increasing level of abstraction. And here's the first one. I want to graph y equals x from 0 to 10. And I want to find the area. Now, this is a triangle, so we know easily this area is 50. Right? We know that. But I'm going to solve it using Riemann sums, which is a much harder way to do it, but it will let us generalize to other shapes. So what I'm going to do is start by drawing 10 rectangles. I won't draw exactly 10, but mathematically we want to have 10 rectangles here. And they all look like that. And they're equally spaced. So the first rectangle stops at 1, 2, 3, all the way up to 10. I need to find the area of each rectangle and then add them all up. Well, this is easy. I mean, we can just do this by looking at it, because this first rectangle is just 1 by 1. And then 2 by 1, and 3 by 1, and 4 by 1, all the way up to 10 by 1. So the area here is 1 plus 2 plus 3, all the way up to 10. So the area is the width times, because the width of each rectangle is 1, the sum of all the heights, 1 plus 2 plus 3 plus all the way up to 10. They all have the same width, so I can factor out the width. And then take the sum of all the heights. And this ends up being 55. Now, in order to generalize this, I'm going to write this same thing up with a little bit more abstract notation. First off, I'm going to name all these points on the x-axis, x0, x1, x2, all the way up to x10. And similarly, I'm going to name all these y-coordinates, y0, y1, y2, all the way up to y10. And I'm going to call the width, which is the same for every one of our rectangles, I'm going to call the width delta x. And I'm going to make a little table that just formalizes what we already know. x0 is 0. That's the first x point. What's x1? And x2 is 2, and so forth. But I'm going to write it this way. Isn't x1 the same as delta x, because it's the width of one rectangle? And then x2 would be 2 delta x, 3 delta x, 4 delta x, because it's just the width of so many rectangles. Does that make sense?
So delta x is the width of 1?
Is the width of 1, exactly. The width of 1 is delta x. 1, I didn't say, yeah, 1 width is delta x. So x2 is 2 delta x, x10 is 10 delta x. There's a lot of overhead for a simple problem, but once we get all this structure in place, we can use it on every one we have to do.
What do you mean like the width? What do you mean like going from like 0 back to 10?
That's delta x, that's delta x, that's delta x. That's what I mean by width. So every width is 1. Was that your question?
Why are we multiplying them by like 10 and 2?
Because 2 delta x is that x value. 3 delta x is that x value because I've come out 3 rectangles worth. When I've come out 7 rectangles worth, I'm over here at 7 delta x. Any other questions? Because if you don't understand the setup, it's going to be kind of messy, so I want to make sure we're okay. Okay, now that we have all the x values, how can I find all these y values?
Delta y plus 1.
Okay, good idea, but delta y in general won't always be the same because your function could be curved.
Okay.
Right? For here, it's the same, but in general, it won't be. So another idea, I think I heard it. Since y equals x, for this equation, it's just the same. So I'll write this. y0 actually is x0, which is just 0. y1 is x1, which is delta x. y2 is x2, which is 2 delta x, all the way down to y10, which is x10, which is 10 delta x. So for this equation, and this equation only, the y's and the x's are the same. But now let's just think ahead a little bit. What if my equation was y equals x squared? Then where would all these numbers come from?
Square x.
Exactly. X squared, x2 squared, x3 squared, x4 squared. So whatever this function is, I just plug this into it. Okay, so now with all this formalism, I'm going to write this area expression the same way. But I'm going to use xOs and yOs and things like that. So the area is the width of one rectangle, which is delta x. That's the width. Times the sum of all the heights. Where are the heights up here? The y's, exactly. So the first y plus the second y plus all the way up to y10. Which is delta x. And now let's plug in what the y's actually are. It's 0, delta x, 2 delta x, 3 delta x, that. Okay, I'm almost done. When I'm done, this is going to look just like that. What can I factor out of the parentheses?
Delta x.
Factor out of delta x. I'm going to not write the 0 because it's just 0. So that gives me a delta x squared, 1 plus 2 plus all the way up to 10. Which for us, since delta x was 1, this is just 1 times 1 all the way up to 10, which is 55. So at the end of the day, this is just a much longer way of writing that. But the reason I did it is because the next thing we're going to do is we're going to chop this up into 20 rectangles. Then we're going to chop it up into n rectangles. And when we do that, it's going to be easier to sort of think about this, because this is more abstract. So we'll be able to think about this. And then we'll see kind of what works, what's going to work for a problem in general. And it's okay if this doesn't perfectly make sense yet, as long as you sort of basically have the idea of what's going on. Okay. All right, so now on the next board, I'm going to do this exact same problem, but with 20 rectangles instead of 10. And I want you to think about what's different. So for 20 rectangles, my area formula that I have over there is delta x times the sum of all the y's. y0 plus y1 all the way up to what? 20, right. And here n is 20, right? All the way up to y20.
Wait, even though now delta x equals 0.5 though, right? So how?
Right, okay, yeah, well, yeah, I haven't even, yeah, so right, so what is delta x now? Yeah, and I'm going to write it as 10 over 20 because it's the length divided by the number of rectangles, right, which is just 1/2. Right, so delta x is 1/2. But isn't all that other stuff still true? That x1 is 1 delta x, and x2 is 2 delta x, and x3 is 3 delta x.
So there's 20.
Except there's 20 of them instead of 10. Exactly. So the area is still delta x times 1 delta x plus 2 delta x all the way up to 20 delta x. So I can do the same thing as before. I can factor out a delta x and get the sum from 1 up to 20. And now we'll plug in numbers and evaluate. But you see, the only thing that changed was now I have 20, and delta x is smaller. So delta x squared is going to be 1/4. Yes,
Isn't delta x 0.5?
same as 1/2.
So why is 1 times delta x more?
I factored out a delta x. I made a delta x squared.
So just stay 1.
Yeah, well, because I pulled this out.
Oh,
Right, so you can see then I added it in here.
oh.
Okay. The sum of numbers from 1 to 20 is 110. So
In your head? Did you already work that out before?
both. There's an easy formula, and we'll see that next. No, it's 210. Thank you. Yeah. 210.
I was doing it in my head. And I
and
got something else.
Thank you. I like having you in the front, Rita. It keeps me honest. Now, let's see if we can figure out what would happen in the general case. So I want to do the same problem with n rectangles, You tell me what needs to change. Starting in the first line, what changes?
Goes to n instead of 20.
Instead of 20, it goes to n. And I'll use a capital N just because.
Wait, are we saying that we have this many rectangles?
Yeah, if I have capital N rectangles, so n could be 1,000,000.
Then, yeah.
So we-
Delta approaches 0, yeah.
This is where you get limit.
Because it would get n small as possibly could.
Okay, but for a fixed n, delta x, it does approach 0, but for a fixed n, what is delta x?
N over,
10 over n.
10 over n. Right, because when I had 20 rectangles, it was 10 over 20. If I had 50 rectangles, 10 divided by 50. If I have n rectangles, delta x is going to be the whole distance divided up into however many rectangles I have. Okay? Any questions on those two replacements? Because that's really all that changes. The rest is just plugging that in, because now, what's different in this line? N instead of 20. So that means this is n instead of 20. Is that still a delta x squared in the front?
Yes.
So that still factors out. So what I have now is delta x squared times, and this is a formula. You may have forgotten it from pre-cal, that's fine. The sum of all the numbers from 1 to n, all the positive integers, is n times n plus 1 over 2. And that probably rings a bell now that you've seen it. N times n plus 1 over 2. So it was 20 times 21 over 2, or 10 times 21. 10 is 5 times 11, etc.
So that's the formula for
1 through
n.
1 to n. Yes. Yes. And now all I need to do is plug in what delta x is. You already told me that delta x is 10 over n. So this is 100 over n squared times, and I'm going to multiply that top out, n squared plus n over 2. One more little algebra step, I'll call this 50 times n squared plus n over n squared. So this formula will tell me, with however many rectangles I have, what my approximation is. So if you plug in 100 rectangles, 3 rectangles, 25 rectangles, this formula works.
That would like 50 n over. Taking that out.
Well, I could take stuff out, but I don't need to right now, because all I care about, if I want to know the actual area, how many rectangles do I need? Infinitely many. So I can't just plug in an infinity, that's silly, but I can take a limit, right? So the real area is exactly equal to the limit as n goes to infinity of this expression.
Can it actually reach exactly 50?
Well, at the limit, sure. So it asymptotically approaches 50. For no fixed n value does it ever equal 50 exactly. But what is this limit? We can all do this, right? Because the degree on top is same as the degree on the bottom, so this limit is just 50, because this thing goes to 1. And we saw that our first approximation was 55 with 10 rectangles, and I got 52.5 with 20 rectangles. So that's going to asymptotically approach as a limit 50, which I know is the right answer because that's the area of a rectangle. And that's the method of Riemann sums applied to a very simple problem. But the nice thing is I did this in complete generality, so if I changed it even to a complicated problem, very little changes here. And the next couple of examples we're going to do, hopefully we'll have time to do about 2, you'll see how very little changes. So in fact, let's do a couple mental exercises. Over there, my triangle went from 0 to 10. What if I went from 0 to 15? What would change here?
15 over n.
That would change to a 15. Would anything else change?
The 15.
Well, yeah, so then when I start plugging in numbers in, right, then the actual numerical values over here will change. But as far as the formula goes,
No.
15 is all that matters. It just changes the width of the rectangles. Because I'm still going to have infinitely many, and they're still equally spaced. Okay, so that doesn't change. What if my function was, instead of x, let's make the function x squared. Where would things over here start to change? The y's are still y's, right? But the y value comes from squaring the x value. So it would be that squared, that squared, that squared. If y equals x squared was now our equation, that's what would change. Now, how would that change manifest itself in this line? Right, good. So those would all be squared, and I'd have an x cubed out there. So in general, whatever formula you have and whatever your upper limit is, it just changes this and that. And the rest of the mechanics work. So we'll do x squared as an example just to see how that goes through. Questions? Okay, so yeah, go ahead.
Is this like the formula, like version of the rectangles? Like,
Basically, yes. Yeah, this is a formula version of the rectangles. And we can make this even more concise using sigma notation, but today I'm just going to write everything out.
How did you get the 100 over n squared from the sum of numbers?
No, this just came from that.
And then you just
Other questions? Okay, let's try x squared from, say, 0 to 1. And what I'm going to do is I'm only going to change the parts that need to be changed, just like you told us. So here's my equation, y equals x squared. The bounds I want to find the area under for this problem are 0 to 1. Okay. Okay. So really all this stuff we've already talked about. And I'm going to use n rectangles. So n rectangles, they're equally spaced. I'm going to draw them the same way. So the x value, if I plug it in and get a y value, that gives me the height. So delta x is the width of one rectangle. How wide is one rectangle? If I have n of them. 1 divided by n. Right. Okay. Now let's look at this table that I had before, and I'm just sort of looking at what changes. I claimed that xo, x1, x2, all the way up to xn, nothing changes except now I have n rectangles instead of 10. So that doesn't change, but the y values do. Y O is no longer XO, it's XO squared. So all these x's get squared. There's n of them. Okay. Which means this is 0 squared, it's delta x squared, 2 delta x squared, all the way down to n delta x squared, and that is quantity squared, so the coefficients are also getting squared. So the area is the width times the sum of all the heights. And the sum of all the heights is what we have written over on the other board. So I'll come over here and make changes as appropriate. And basically, I'm just going to recap what we just said about this. So the area is the width times the sum of all the heights, which is all the y values. This is basically true for any equation. But since delta x is 1 over n, I plug in all my y values, and it's 1 delta x squared, 2 delta x squared, 3 delta x squared. The greatest common factor here is an x squared. So when I pull out an x squared, that gives me an x cubed in the front. And then what's left is 1, 2, 3, 4, but all those numbers squared. Any questions at all up to this point? Because now we're up here, all I have to do is, hopefully there's a formula for the sum of the first n squares that we learned in pre-cal, and there is. So we'll plug that in, plug in what delta x cubed is, take the limit, hopefully it will give us the right answer. So delta x cubed is 1 over n cubed. And the formula for the sum of the first n squares is n times n plus 1 times 2n plus 1 over, do you remember it? 6. Close.
And there's like 1 over 4, right?
The next one is over 4. Yep. Yep.
I remember that.
You remember them. So this is the area for any number of rectangles. But to find the Riemann sum, I want to actually take a limit as the number of rectangles approaches infinity. Hopefully this will converge to a finite value, and that will be what we define as the area under the parabola. So let's take the limit as capital N goes to infinity of the area. And can you tell by looking at that what it's going to be? What's the degree on the top? Cubed, actually, right?
3 on the bottom is cubed up.
And it's cubed on the bottom. Not 1/6.
1/3.
2/6. Because imagine multiplying this out. You're going to get a 2n cubed plus some other stuff, right? So 2n cubed plus some other stuff over 6n cubed. And that is 1/3. 1/3. Because it's the leading coefficients. I don't care about the lower order terms here, the n squared, the n, the constant.
Wait, finding the coefficients, what does that give you? That gives you, wasn't that how we found that the vertical asymptote or something?
Horizontal.
Horizontal asymptote?
which is the limit, right? That's what a horizontal asymptote is. As n approaches infinity, where does the function level off?
All right. Okay.
Now, if you are coming from AB calculus, you will recognize that what we just did is the same as evaluating this definite integral. And you can check that that's going to be the same thing. If you're coming from analysis, don't worry about that. We'll see that in 2 days. Now what I want you to do to see if this makes sense is I want you to find the area under x cubed from 0 to 3. X cubed from 0 to 3.
So wait, what if that one was not n to infinity?
Well, see, it has to be to infinity because I'm finding the area, and the way I find the area is basically I use infinitely many rectangles. So my last step is going to be computing that limit.
So you get an infinity.
So I need to go to infinity.
Got it.
Right. X cubed from 0 to 3. I'll let you work on it, and I'll write up on the board the things that are changing.
How would that equation change?
And that's what I'm going to write. The sum of cubes formula is up here. You may find that helpful at some point. Let me see. Yes.
So isn't it like? Oh wait, is this?
We don't have 3 rectangles. We have n rectangles.
I thought we were doing it. You said 3x from 1 to 3.
Those are your bounds from 0 to 3. You're still using n
Oh,
rectangles.
okay, sorry.
check your arithmetic.
Wait, for those formulas, do we have to memorize those?
I'm going to give you a shortcut.
Okay.
81 over 4 is the final answer you should be ending up with. And basically what happens, the only thing here that changes is the cube. So my area is delta x times the sum of all these things cubed. Delta x cubed plus 2 delta x cubed all the way up to n delta x cubed. So an x cubed gets factored out, and then I have left the sum of all the cubes. So delta x to the 4th, 1 cubed plus all the way up to n cubed. Delta x, for this problem, is 3 over n, because I wanted the integral from 0 to 3. So it's 3 to the 4th over n to the 4th. And I know this sum is n squared, n plus 1 squared over 4. And if I take the limit as n goes to infinity, because this is my area for a finite number of rectangles. As n approaches infinity, that's squared and squared, so that's degree 4. That's degree 4. The quotient of the coefficients is 81 over 4, which is my area. Again, AB folks can verify that the integral of 0 to 3 cubed is just x to the 4th over 4 from 0 to 3, which is 81 over 4. So we found the area. So clearly, I could, in general, use this method for x to the 4th, x to the 5th, etc. And if I can do all those polynomials, couldn't I find the area under 4x cubed? Wouldn't it just be 4 times this area? So I could find the area under, say, 8x cubed minus 2x squared plus 4x plus 3. I could do that by finding this one, this one, this one, this one, all separately, and then just adding them all together.
Would that work? Same thing with the integration of this?
Sure does. Yes, same thing as integration. That would work. But what's not clear is how can I do higher powers, like x to the 4th, x to the 5th? What is that formula for each problem? Because I've told you what the formula is for cubes, up to cubes. But other than that, the formulas get kind of complicated. But here is a handy little fact. The sum of the k powers, so cubed or squared or whatever, the sum of the k powers is equal to, well, writing down what it is for a general k is complicated. But all we care about is that leading coefficient, right? I don't care about every single term. Well, it turns out that this is always n to the k plus 1 over k plus 1 plus lower degree stuff that I don't really care about. And this should look very familiar to you. Where does this expression show up? Integration of the power rule. This is why that's the formula for integration of the power rule. Because the sum of the kth powers is n to the k plus 1 over k plus 1 plus some lower degree terms. Hey, wave to the camera. So if you had a problem with higher degree powers, you could do it using this method. So with that, for homework tonight, I just want you to look at 2 problems, but write them all the way out, just like we did in notes. I'll write them up on the board.
Pardon the interruption, but we have just a couple of quick announcements for this morning. The Romney-Ryan campaign is offering internships and looking for student volunteers in the Riemann campaign office. If you're interested in getting involved, getting service hours, or meeting elected officials and learning firsthand